This is the second video in section 7.3, complex numbers in polar form. The idea here is we want to see how expressing these complex numbers in polar form actually makes it pretty easy to compute with them in many ways. So first though, I want to remember that if I have two complex numbers, z1 is a1 plus ib, z2 is a2 plus ib2, then we can multiply these, right? We can just multiply them like we saw above and really just FOIL them out. And we get some result. If you remember, let's scroll back up and just reference that result. When we do multiply them, yeah, here's what we end up getting. We get this big mess, right? Which is fine, but it doesn't give us any intuition about what multiplying two complex numbers really tells us about the result. What does this result tell us about z1 and z2? Well, if we're just multiplying real numbers, we have some way of thinking about multiplication. 2 times 3 is adding 3 to itself twice, or adding 2 to itself 3 times. But what does it mean to multiply two complex numbers and get this weird result out? So we're going to see that with complex numbers expressed in polar form, we can actually get a pretty graphical sense of what complex multiplication does. So let's not go through this further, but let's think about what would happen if we multiplied two that were in two complex numbers in polar form. So that's what this little fact here is telling us about down at the bottom of my page. It says if z1 is r1 times cosine 1 plus I sine theta 1. In other words, the modulus of z1 is r1 and the argument is theta 1. And likewise for z2, defined this way. Then when you multiply them, it turns out you really are multiplying their modulus, their moduli is the plural, out front, and just adding their angles to get this new result, right? The product of the two. It turns out dividing is very similar. You're just dividing the moduli and then subtracting the angles. So I want to see here that at least how could we somehow show or work to seeing that this is a believable statement? I don't want to go through all the details, but how would we do this? We'll just take your z1, let's say it this way, take your z1 times z2 in polar form, and here's my second one. This is z2 I'm writing down. Take those in polar form, multiply the r1 and r2 that are just factors in there that are easy factors, multiply those out front, and then FOIL what remains, right? FOIL this cosine of theta 1 plus I sine of theta 1, and the cosine of theta 2, I sine of theta 2. Well, if we go ahead and multiply these two out, just following that formula for multiplying two complex numbers, at the end of the day, we could see that we're going to end up with, or even just foiling it, maybe we see this for ourselves. I'll FOIL these out. Lots to do here. Finally, the last things that get multiplied are I sine theta 1 and I sine theta 2, and that makes I sine theta 1, I squared sine theta 1 sine theta 2. And remember, I squared, that's just a negative 1 there. So let's actually think of getting rid of that I squared and just think of it as a negative. This is sine theta 1 sine theta 2. And this is all in my parentheses. Then we can put together the real and imaginary parts. The real stuff is the cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. from where that I squared used to be. That's the real stuff. That's the stuff that isn't attached to an I, but the rest of it is attached to an I, so let's factor that I out of the rest of it. And now what do we have? Well, by our identities for angle addition, this is just cosine of theta 1 plus theta 2. That's our real part if we use that angle addition formula for sine, for cosine. And likewise, this is just the same thing for sine. So we get exactly what we expected, or what the result down here tells us. If when I multiply the two numbers, I'm really just multiplying their moduli and resulting in some new modulus, right? You can think of this as being like, I don't know, R. And you can think of this as being like, I don't know, big theta and big theta. Then we're seeing it's still in polar form. The product is easy to pick apart. The modulus of the product is capital R, the product of the two little ones. And the new argument of that product is the sum of the two individual arguments. So what does this mean? We've just shown here that this is believable. How you do division is actually kind of complicated, but maybe we'll get a hint at how that would work later on in this video. But what does this actually mean? Let's erase up here. We've seen how we can come up with this result. Let's erase and see, what does it all mean? Well, let's do erase there, but I need this space. Okay. So what does it all mean? It means if we've got two complex numbers, let's say one has, I don't know, an angle of pi sixths and another has an angle of pi fourths in polar form. Let's make this one maybe a little further out, or maybe actually closer. So let's say this is like z1 and this is z2, and let's say the modulus of z1, so the distance from the origin, is 2, and for this guy it is 4. This guy's twice as far as the other guy. Or maybe it's more believable that this would be like a 3 from my picture. Then all this multiplication is telling us is that if we multiply these together, call the result maybe just z. Let's let z equal the result of multiplying these. All we have to do is multiply the moduli and then add the angles. Pi fourths plus pi sixths, that's 6 plus 6 is 10 pi 24ths, or what, 5 pi 12ths? So that's fine, but what does this mean? It means when we multiply these two numbers together, the result is just the distance one is angularly from the x-axis, from the real axis, plus the distance the other one is angularly. You add the two angles. So I'm going to go think of pi fourths plus a pi 6 more from the tip of there. What would that take me to? It's going to be 5 pi 12ths. So it's this direction. Oops. It's a very narrow angle here. Here, let me redraw this. Maybe that's our 5 pi 12ths. Right? When we added the two, when we multiplied the two complex numbers, the result is going to be an angular distance that's the sum of these two, so multiplying them adds their angle and multiplies their moduli, right? The new modulus is 6, so it's 2 2 times 3. So it's 6 units away from the origin. I'll just say that's 6 units away. I'll say that's 6 units. Right. So that's what multiplying complex numbers really does. It adds their angles. You rotate, you go to the position of one, rotate even further by the argument of the other, and then go distance from the origin that is the product of each of their individual distances from the origin. So the moduli multiply and the arguments add. That's the big lesson. And for division, it follows a very memorable pattern. For division, the moduli divide and the arguments subtract. You're just rotating in the opposite direction. So let's go through these really quickly here. Given z1 equals 20 cosine 30 plus I sine 30, z2 is 3 cosine 210, I sine of 210. Find the product and write it in polar form. Easy. That's essentially what we did up there. z1 times z2. Multiply their moduli. Right? These are both in polar form, so we know how this works. Multiply the moduli and add the angles. 30 plus 210 is 240. Okay, done. That's easy. That's in polar form. Dividing is no worse. Maybe you have to subtract some fractions for the angles, but it's still no worse. Let's do this. If I want to divide, remember we divide the moduli, z1's modulus over z2's modulus. That's the 8 out front and the 2 here. And we subtract the angles, top minus bottom. The argument of z1 minus the argument of the bottom, z2. So this is what I was saying. It might be a slight bit more complicated just in the arithmetic, because you actually do need to subtract these out. But it's not too bad. Pi fourths, remember that's just 3 pi twelfths. Subtract, you get 4 pi twelfths, which is pi thirds. 8 over 2 is 4. Subtracting the 7 pi twelfths minus pi fourths gave us 3 pi twelfths. 7 pi twelfths minus 3 pi twelfths. Which is 4 pi twelfths, which is pi thirds. So that's our new argument. And that's in polar form. We can see the angle, pi thirds, the argument of this quotient, and the modulus is 4. Okay, let's do another one a little bit different here. Given these guys in rectangular form, compute the product and write the product in polar form. Well, you have options here. You could just multiply these by each other. Right? You could just multiply them out. Or you could multiply them out and then try to convert it to polar. Or you could convert to polar first, and we know multiplying there is very easy. So maybe I'll convert to polar first. And if I look at z1, this is saying we go a half in the real direction, root 3 over 2 in the imaginary direction, and that's where our point sits. Well, what is this? When our x is a half and our y is root 3 over 2, we know that is the pi third special angle on the unit circle. Right? So we know how to describe the coordinates of this guy. The xy coordinates are already cosine of pi halves, sine of pi halves. Right, so we know the argument, not pi halves, sorry, pi thirds. So we know the argument must be that pi thirds, that angle we have to get up to the ray containing this guy. And furthermore, we also know right away that this guy's modulus is 1. It sits on the unit circle. Right, these special angles, these special ratios we get, a half and root 3 over 2, those are from points on the unit circle from trig. So we can say z1 is really modulus times cosine pi thirds plus I sine pi thirds. z2, I'm going to do the same way. You can think of it very similarly. It's this triangle instead, but we know that's just the pi sixth. Triangle. Again, that's going to be on the unit circle because these ratios come out nice that way. Root 3 over 2 and 1, those are sine and cosine values, must be on the unit circle. So we know for Z2, the modulus is also 1. This is Z2. It's just a different angle. Pi thirds in this case. So multiplying these numbers is trivial now. Z1 times 2, Z2, you just multiply the moduli and add the angles. And of course that's just 1 times cosine of pi 6 plus pi thirds, that's pi halves. It's 90 degrees. So there we have it in polar form. All right. You can see the modulus out front, 1, and the argument pi over 2. Right, so using those formulas isn't too bad, but they lead to a very nice fact, since exponentiation, raising to a power, is just repeated multiplication by the same thing. You can easily apply that sum formula, or the multiplication formula, to get this power formula. Right? Z times itself n times, that's z to the n. That would say you have the same complex number multiplied by itself n times. Well, you're going to be multiplying those moduli by each other n times and adding that angle to itself n times. Adding an angle to itself n times gives you n times the angle. Right? So this is essentially just saying that if we multiply a bunch of times, n times, we'd have to take the modulus of z and multiply it together at n times. And we'd have to add those angles together n times. Plus the same in the sine part. Right, that's just from the multiplication formula that we saw above. Well, r multiplied by itself n times is r to the n. Theta added to itself n times is n times theta. So that's how we get this theorem, which is called de Moivre's theorem. It's a very useful one. It comes up a little bit later in mathematics as well. But we'll see it becomes very easy to compute something like this weird complex number here, 2 times all this stuff in polar form raised to the 4th power. Let's write the result in rectangular form, a plus bi. Well, by, let's call this z, by de Moivre's theorem, it's called z to the 4th actually. This thing to the 4th is really just the modulus to the 4th times cosine of 3 pi 16ths times 4 plus I sine times 3 pi 16ths times 4. Right. All we did was raise the original modulus to the power that we had and multiply our argument 3 pi 16ths by that power as well. And if we multiply this out, it looks like we get the original expression. Well, let me keep it going here. 2 to the 4th, that's 16. Let's see what we have. Cosine of cancel, cancel. It looks like we have 4 left down low. So it must have the same thing in the sine. And cosine of 3 pi 4ths, that's just second quadrant. That should be negative root 2 over 2. Sine in that quadrant, again at the 3 pi fourths, is going to be root 2 over 2. Multiply the 16 through everything, we get 8 root 2, negative 8 root 2 plus I times 8 root 2. So that's what our number z to the fourth equals. This stuff we started with. To be clear, I'm saying all the polar number inside of this fourth power, I'm calling that z. So all this stuff to the fourth is z to the fourth. That's how I'm labeling here. All right, so it might be a good time to pause and see if you can finish this last problem here. It's saying compute this and write the result in rectangular form, just like we did the last, except the number being raised to a power is not yet in polar form, so it makes it harder to use de Moivre's theorem. You could FOIL this thing out with itself 6 times, right? 6 powers of this. That's a mess. Don't do that. Convert to polar and then use de Moivre's theorem. So let's try to convert this. Let's call this number inside, let's call it z. So we want to know what z to the sixth is. But first, let's figure out how to express z in polar. Z in polar. Well, let's see. We've got the real part of z, which is like our a value. That's 2 root 3. The imaginary part, which is like our b value, that's 2. So right away we can get the modulus of z. We remember that formula, hopefully. 4 times 3 is 12, plus 4 is 16 inside the root. Modulus is 4. Not so bad. We still need to know what the argument is, so this is where we're going to use the tangent theta. In regular polar coordinates, it's y over x, but here that's just imaginary part b over real part a. This is 2 over 2 root 3. It's 1 over root 3. So you have to think about what angle makes tangent equal 1 over root 3. I'll let you work on that on your own, but maybe pause it if you want to work that out. But I'll also skip to the punchline. That means theta has got to be sines like a half, cosines like root 3 over 2. It's got to be pi sixth. Okay, so there it is. We have our argument. We have our modulus of this number being raised to this power. So I can say z to the sixth is really just the modulus 4 times cosine pi sixth plus I sine pi sixth. All that raised to the sixth power. Well, so this is easy to write. This is 4 to the sixth times cosine of, now we multiply the angle, the argument, by 6. So let's see, this is some terrible number. What do we get? 4 raised to the sixth power. I get 4096. 4096 is that 4 to the sixth power. And notice, pi 6 times 6, that's just pi. Sine of pi is 0, so this imaginary part is falling out completely. Cosine of pi is -1, so our answer is -4096. 2 root 3 plus 2i, something involving complex, when raised to a power, becomes purely real. Kind of a strange idea. Okay, that is it for this video. We'll go into the next section with the next video.